Welcome back to the series of videos Get on the Right Frequency. In this video we are going to cover the modal frequency response analysis. So just as a small reminder, this is the formula for the natural frequency, where if we increase the stiffness, we are going to increase the natural frequency, and if we increase the mass, we are going to lower the natural frequency. So in order to start in this analysis, there are three things that we need. First, the natural frequency eigenvalues that are going to give us an idea what is the range of frequencies that we need to evaluate. Second is to check the percent modal effective mass from our normal modes analysis to make sure that we are capturing all the frequencies that we want and the frequencies that are important for our system. And if you need to know from where to take a look to that, you can see this video above in here. And number three, you need at least one load. So let's jump into the setup. So what I did as I run the normal modes analysis, for example, what I did was to duplicate the analysis, and then that's going to catch up all the idealization, connectors, surface contacts, and mass properties, concentrated masses, and even the mesh. So that's going to help us to move quicker to the objective of these results. So the first thing that we need to notice is that under the subcases we have two extra things to configure. So one is the damping, and the second one is the damping setup. The modal setup is going to be the same one that is coming from your normal modes analysis. That's totally fine. And the damping is something that you cannot skip. You need to use some value of damping. If not, the results are going to be invalid and unrealistic at all. You need to have damping. You can define it by Rayleigh damping theory. You need to find the alpha and the beta, or you can use the modal damping that is just requiring the percentage of the critical, yeah. So that value can be around no more than 5, let's say, in most of the cases. So for example, in this analysis, I did this comparison in between 5 and 2%, and the difference was not a huge deal. So I would say it is acceptable to run first at 2 if you find the things that are the results are not matching or not making sense. You may investigate a little bit more in there. Then we have the dynamic setup. This one is where the magic happens. So you need to set the lowest frequency, the highest frequency. This is going to govern the range that is going to be shown on a plot later. And then you have the types. You can select from discrete frequencies, frequency range, that is the one that I like, cluster between modes, and spread around modes. So let's concentrate in this one. So I got the lowest frequency that I want to evaluate. This one can be same as in here, the frequencies limits, and it needs to be a little bit higher, or it can be the same, but not lower. Then you have the highest frequency that, well, in my ones it is matching, but you can have it below the highest frequency, of course. Then we have the number of points in the range. So it is going to be as simple as the number of frequencies that it is going to calculate. And based on that number and based the difference in between frequencies, you're going to have the frequency increment. That is basically saying that every 1.5 Hertz, I will have a result. So that's it. So we can make it match to 1. So I will have one frequency per each hertz. But yeah, and you can add several of them. If you have, for example, in this small graph that they show, for example, if I have one frequency far from the other, I do not need to check the entire frequency range. I can just go exactly to the ranges that I want to check. In this case, for this video, I'm checking the entire thing because I want to show you how damp and undamp system can make a huge difference on your results, not only in magnitude, also in the amount of frequencies that are going to be critical. Okay, so as a good reminder, this type of analysis is about to find disturbance on the system that in combination with the natural frequencies are going to create resonance. So we want to avoid that thing to happen, of course. That being said, there is interesting things that we need to take in account. That, for example, well, as I said, I think not all the frequencies are going to create a problem. Maybe those are going to be just noise or small vibration, so they can probably not be considered as critical, but that's why we run this kind of analysis. The other thing that is important is that the way how the system is loaded has an impact on the behavior due to the phase of the load. So the phase of the load is sometimes something that we need to play around, especially if we have two motors or several factors that are adding vibrations to our system. That kind of things can happen. So for example, here I have a dial indicator touching my machine here at the front in this base, as you can see. So I start to ramp up the speed. I was looking for a spot, so I was there close to the 200 Hertz. So as you can see, I started with this magnitude, and then suddenly it becomes to zero, and then, well, I push back the frequency to try to find again the same spot, and the result is that it was larger. So maybe when you turn on the machine, you see no vibrations, but when you turn it off, you potentially can see vibrations. So that's something that needs to be taken in account. Okay, so from this kind of analysis, remember, we can get true stresses. We can also identify excessive motion, vibrations, and potential noises, right? So there is no plot specific for noises. We have just Hertz, but we can find those spots. While I was running this test on my machine, I found that some of the frequencies that on normal modes was suggested to be a normal mode, those were points where, well, yeah, we have some vibration, but more importantly, they were very noisy. So let's talk about accuracy. There is a tip that is important, and it is called the residual vector. So residual vectors is a general option that can be included on the design, on the analysis, and it can increase our confidence on the results that we are obtaining. So in order to include it, we go to parameters and just type here resvec. Resvec. There you go. So the default is auto, and based on the documentation that I was showing before from Autodesk, if you have it on auto, it is going to turn on only if you are including a force that is an enforced motion. If not, it is not going to turn on. So the recommendation is to come here and turn it on to make sure. So in my design, in this case, it didn't add any like huge difference, like saying like, oh yeah, of course. But yeah, it is giving me confidence on what I'm having. Looking at the results, we have an XY plot sections, right? So there is by default one that is named maximum displacement magnitude versus frequency. So remember, the domain of this analysis is under the frequency, as you can see here below. And we have a maximum displacement, and we can see the results just by locating the cursor over the curve. And as you can see, I have 211 Hertz as my worst case. And now that I'm here, I want to show you that in order to take all these results and extract them to an Excel file and play around with the results, comparing, and etc., what you need to do is to copy data to clipboard. That way you obtain the data that is just need to be pasted on Excel and then create the table. So let's take a look to this graph. This one is showing an undamp, that is clearly the one that is having a huge magnitude of more than 40 millimeters, and the one that is damp. So there are many things to see in there. One is that the damp is removing the other frequencies that was suggested by the undamp system. So those other ones are more matching on the noise thing that I told before, that I was playing around with my machine, making the measurements. So this helps us to concentrate only on the frequencies that are potentially a resonance effect. As well, it happened to me. Here is the result of a machine starting to enter in resonance. Fortunately, I was in front of the machine and I were able to turn it off. But if not, who knows where that machine was going to end. So, and with the help of the strain energy density plot that is at the normal modes analysis, I should be capable to identify those areas that require to be stiffened. So if you need also to check that information, you can see here the first video of the series.